In this video, we're going to cover some of the important components of our linear momentum and collisions, chapter number 8 from our textbook. The crash course video on collisions is already posted in the extra video section of the class on Brightspace, but I'm not sure if this video is this flipping physics video. So I'm just going to pause here for a second and give you a chance to write down this address. I think it is case sensitive, so if you're going to go to this video, make sure that you capitalize where necessary. All right. I like his videos. He's an AP physics teacher that does a really nice job of summarizing and um, really nails down procedures for some of our problems and descriptions of scenarios as well. Well, here we are in chapter 8. Last week was chapter 7, and in chapter 7 we were talking mostly about kinetic energies and potential energies. And in the kinetic energy example, or specifically, we noted that we can compute the amount of energy that an object has when moving in a straight line with this formula here. An object's mass times its tangential velocity squared times 1/2. Now, the speed of the object is used in this computation. We're using velocity here, but the interesting thing is that speed is the component of our concern, because if we had like a negative direction, for example, associated with our velocity, the negative quantity ends up being squared and disappears from the computation. And because that the direction that direction sign can be lost when we compute that, then we lose a little bit of information about the behavior of an object. So a new quantity was invented or was represented with a different equation so that we can maintain the directionality of the object. And that's what we call momentum, in this case linear momentum. And we'll define momentum with the lowercase p, and it's the product of mass times velocity. We're not going to square velocity, we're just going to multiply mass times velocity, and that's what we're going to call our momentum. And you should note that momentum is reported with a lowercase p with an arrow. It is a vector quantity, so momentum is a vector quantity, not to be confused with capital P for power, or the Greek letter rho for density. We're going to talk more about that in a later unit. These two both look like the letter P, but again, we're specifically interested in the lowercase p with the vector hat. So lowercase p for momentum. All right, now the unit for momentum, if we have mass, which we're going to use as kilogram, and if we have our velocity, which is a meter per second, we would note that our unit for momentum is a kilogram meter per second. But also, we could use a little bit of mathematical trickery here, and we can report a kilogram meter per second squared multiplied by a single second. And the unit from this second in the numerator cancels with one of these seconds in the denominator, and we again have kilogram meter per second when we're done. This, of course, is the representation of a Newton unit times a second, so we can call this a Newton second. Interestingly, with the with the constructed units in the last several chapters that all had a special name to them, this one does not. There is no special name for the unit for momentum. Now, while both kinetic energy and momentum are measurements used to quantify an object's mass moving with some velocity or speed, it's momentum that gives us the ability to kind of predict the results of impacts. For example, when we have velocity involved with the mass, we can see some interesting computational results from that. So if we recall that an acceleration of any body is equal to the change in velocity over time, we could report that as a final velocity minus an initial velocity divided by a change in time. And we might also note, with the introduction of a mass times this acceleration, so this was our acceleration from the line above, a mass times acceleration does represent a net force acting on a body. Well, by distributing this mass into our velocity values in the numerator here, we get this mass times velocity final minus mass times velocity initial. And as we just said a moment ago, mass times velocity is a momentum. So we have our momentum final and momentum initial. Now, before we get into our discussion on that, the summary notes from Cincinnati State just wanted to point out that at this point, if we have our mass times velocity final minus mass times velocity initial, we could effectively multiply this change in time, or the time that it takes for this impact to occur, multiply it by a force that's providing that change in momentum, and we have this net force times time equals the difference in momentum. And we call this difference in momentum or change in momentum impulse. And sometimes we use a capital letter I with an arrow because it is also a vector. So we use letter I for impulse, but sometimes J is used. So a J with a vector hat is also sometimes used. Although that can be a little bit confusing because capital J is used for joules. In this case, in this context, J with a vector hat is used for impulse or the change in momentum. And we have an example with a baseball coming up here in just a moment. And now we can see with the change of impulse, which, by the way, since we have a Newton second for each of these two momentum units, then Newton second would also be the unit of measure for impulse. But now with positive and negative quantities allowed, and even directions such as theta values allowed, this really helps us describe what's the effect of an impact of an object with another, or multiple objects for that matter. So when we do get into those computations, we're going to note that we're talking about the sum of all forces, or the net force of the impact. And we're also going to clarify here that in our class, since it's an algebra-based class, we're going to talk about the average force of impact for the duration of the impact. And I'll talk more about that in just a second. But before we get there, I just wanted to point out this screenshot. This came from the Flipping Physics video, and I think he did a really nice job of describing where this change in momentum over time formula is coming from and how it's the sum of all forces. This notation here, again, is a sigma notation. Now, I usually write it like this. That's how you'll usually see it typed out, but that was his handwriting on the board. And this sigma, or the sum of all forces, implies that we're talking about a net force. So this symbol here is just like saying that it's a net force. All right, so the impulse momentum theorem kind of gives us some information about the game of baseball, for example. Other sports, of course, can utilize this as well, but our textbook went with this baseball player as an example. So we'll note that momentum is equal to mass times velocity. And so if momentum is described as mass times velocity, then our change in momentum would be a change in a mass times velocity. Now, mass itself won't change, so we'll note that the mass remains consistent and the velocity itself changes. And also, as a side note, we're going to use the letter J here, our impulse, to describe this change in momentum. So we might note that this is mass times our velocity final minus velocity initial for the duration of an event. And we're also going to pull in this other definition here, that impulse, our change in momentum, could also be reported as our net force times the change in time. So our net force, and I'll put a little average hat here along with the vector hat. So the average net force for the duration of the impact times the change in time is another way to describe the relationship between these objects. So now we have some interesting formulas and functions that we can work with. Here we have a force variable, a time variable, mass, and velocity variables to which we can solve for any one of those components, provided we had enough additional information. So if we knew, say, the mass of the baseball and we knew the velocity of the baseball as the pitcher threw it and the velocity of the baseball after the bat hit the ball and the ball was sent in the opposite direction, we'd have two different directional quantities here for velocity. That product would represent our change in momentum or our impulse. And that's a fixed number. But what's interesting is that there are two variables or two quantities that we can use to adjust or to compute that fixed number of impulse. We have the force that's being applied to the object and the time during which the impact occurs. Now, if you think about a baseball bat making contact with a baseball itself and watch that in slow motion, you could actually see the baseball deform and maybe even the bat reverberate a little bit. That'll give you kind of a visual clue of what's happening during an impact or a change in momentum or this impulse. But you can also see how time is necessary. There has to be a period of time for the change in momentum to occur. Now, if the change in momentum is a fixed number, an object's, like we were saying, the mass of a ball times its change in velocity, that's kind of a fixed number. The two different ways that we can accomplish that, especially when we're thinking about car crashes and why airbags were invented. If we're taking an object's mass, like a car or people in a car, and their velocity going from some fixed speed down to zero, the impulse doesn't change. That's a fixed number, but there are a couple different ways that we can change those objects' momentums. We can apply a really large force over a short period of time. That's what this image is meant to convey here. We can have a big force applied to the object over a short period of time, and that would be a bad thing in a car crash. Or we could try to increase the amount of time of the impact, and therefore we would decrease the force of impact or the average force of impact on the occupants in that car, which is, of course, something we would want to do. So with these airbags, what they tend to do is they inflate rapidly so that when you make contact with, say, the steering wheel or the portion of the car that's protected by the airbag, they deflate and they slow, or they require more time for you to come to a stop rather than an immediate stop by bumping into something that's very hard or harsh end there. Same rules kind of apply to crumple zones in your car. Why we have crumple zones is because as the vehicle collapses, as the components of the car collapse, that increases the time of the impact, therefore decreasing the amount of force felt by the occupants. Now, the last big topic that I wanted to address here in this video was that we're using average force in our class here. But typically when we experience an impact, right at the beginning of the impact and the end of the impact is where the force that's being felt is at its lowest. Right as an impact starts to occur, the force itself ramps up really high to a peak. And then as the two objects that are colliding, as they relax a little bit, the amount of force in between those two objects tends to decrease. So more often than not, when we see an impact, we generally will see a force curve over time. But to analyze this force curve, we would require the use of calculus, because here we have our Newton units across our our y-axis and our time components along our x-axis. The product of these two units, newtons times seconds, ends up giving us impulse or momentum. Well, since we don't all know how to integrate a force curve over time, what we end up doing instead is we calculate or we predict or we work with a value and assume that it's the average force that's been endured over the duration of the event. So in reality, we have a real spike in the data here, but when we compare the area of this rectangle, which represents a flat and constant force for the duration, the area of this rectangle is roughly the same as the area underneath this bell curve or force spike. So if you're interested in seeing how or why the integral against a function of force would work, I'd be happy to share that with you. But for us in this class, we'll most likely just be working with average force for the duration of an impact. So I think that's a good stopping point for this part of the video. I'm going to record another video where we start talking through the examples from the textbook. Thanks for watching.